Assalamu alaikum. Welcome to the series of lectures on advanced computer architecture. In a couple of earlier lectures, we are discussing the pipeline architecture. We discussed with reference to SRC, our simple risk processor. We modified the unpiped architecture to its pipeline architecture, with the example of having 5 stages. In these 5 different stages, simultaneously we could have at most 5 instructions in these 5 stages. In the last lecture, we discussed how to describe the structural RTL functions of different stages. For each stages, the activity was described along with what is being done in every stage, along with which control signals are required. So we assume that the control signals have been generated at different stages. Now, additional hardware which was required was in the form of some additional pipeline registers interfacing different stages and some additional multiplexers. And as a consequence, we had different control signals which are required to be generated. And these control signals were not present if the pipeline architecture is not used. As a result, we have, through pipeline architecture, a higher throughput, but somewhat more delay or latency is increased. Now, we also discussed in the last lecture what are the hazards corresponding to the pipeline architecture. Now, the hazards usually would occur when a particular instruction requires the result from a previous instruction, and that previous instruction has not yet written the results into a register, for example, or into a memory location from where the next instruction or the following instruction requires that data. And that results in an example of what we call data hazards. We have other hazards like for branch, there is some delay involved in calculating the address which is to be pointed out as a result of a branch instruction. Now, we discussed and we had written in RTL form the detection of hazard and also how to correct this hazard. We went into some detail and we said that in the case of data hazard, the detection would depend on what type of different instructions are there in the pipeline. For example, if there are 2 ALU instructions, one after the other, then one instruction, if it requires the output and it has to give the result to another instruction which follows, then there would be an hazard. And this hazard could be avoided by putting some additional no-op operations. And these no-op could be done or introduced either through hardware or through software. In the case of hardware, the data path needs to be modified and 2 functions, that means detection of hazard and secondly the correction of hazard, is to be implemented through hardware for this SRC. We considered a very simple example of having an add and subtract instruction one after the other. The output of the add is written into a register which is used by a subtract instruction. So what happens when the add instruction is in stage 3, that is the ALU, the output is still not written into register given by RA as placeholder. So what we do, we just push this particular instruction of add into the next stage and next, and then install stage we just stall the stage 1 and stage 2 by suppressing the clock, or by just having that particular instruction not traveling to the next stage. That means the instruction subtract, for example, remains in stage 2, and the next instruction, which could be, for example, a shift instruction, remains in stage 1. And when the instruction add just leaves the pipeline, that means just a virtual stage 6, we say then we have the results available for the register required by the subtract instruction, and we let subtract instruction move to the stage 3. As a result, a maximum number of no-op, or bubbles you could say, introduced would be 3 in this case. Now it depends. If there was an instruction which does not require a register to be written, then there would be no hazard in that case and no stall would be required. So for this particular example which we discussed, the solution was, after detection of a hazard, a data hazard, we stall an instruction and keep that stalled in that stage. So there is a staller and a stallee. So therefore the add instruction in this case was the cause, because it has to give some result, and this result is not available as yet. Okay, now this was one possible solution of overcoming the data hazard. Now, stalling is not the only solution. We said last time that data forwarding is a possibility, which means that the data required could be available in an earlier stage than the later. For example, it is not necessary that the add instruction leaves the main pipeline and then we fetch the data from the register. Now, this data could be available in somewhere at an intermediate level in some buffer register. So the data forwarding concept takes this data and feeds it back into an input of the required multiplexer or input of an ALU unit. So this is the basic concept of the data forwarding. Now, in order to understand the data forwarding concept, we need to know which stage would provide the data, and that again would depend on the type of instruction. As an example, the ALU instruction like add or subtract in the third stage, once ALU gives a result that puts into the buffer into stage 4, that is at the interface of stage 3 and 4, the result would be available at the trailing edge of the clock cycle. So therefore, we could pick up and get the data from there and feed it to the previous instruction. Now, to make that more meaningful and to understand this, we need to define the distances among different instructions, and that would be illustrated in the next slide, and we will see that what would be the maximum and minimum distance between different instructions, different classes of instruction, ALU and ALU instruction, and so on between ALU and branch instruction. So the concept of the distance, minimum, typical, and the lowest distance is illustrated in the next slide. Let us have a look at this slide. This slide shows the data dependence distances. Along the top caption, we see a write to register file, and it's the data available in a normal fashion / the earliest stage. So in the entries, we will see that at which stage the data is available or it is written into the register file, and what would be the earliest stage where this data could be fetched from an intermediate register. For example, in the first row and the first column ALU 6/4 means that in the destination register, normally the data would be written at the trailing edge of the fifth stage, which is a register write stage, which means that that particular instruction just leaves the pipeline and we name it as stage 6, considering it as a virtual stage 6. However, this data after ALU operation is written into the register which is available as an input to the fourth stage and which is available in the register Z4. Exactly in the same way, for a load instruction, the data is available latest in the sixth stage and earliest in the fifth stage, which is a register write stage. For load address, it is 6x4, and for branch with link, it is 6x2, since the branch condition is evaluated in stage 2 and that data regarding the address for branch and link instruction would be available in stage 2. Now in the first vertical column, we have now different classes of instruction, and this would mean that we have a read from the register file. The first entry indicates the availability of data in a normal fashion, and slash earliest stage where it would be used for the operation. Let us illustrate for ALU. The first column indicates 2x3, which means that an ALU instruction, which is both a reader as well as a writer of data, would need an operand, and this would be required in stage 2, operand fetch stage. However, after fetching these operands would be used in the next stage, which is the third stage. So even if these operands are not available in stage 2, we could have these operands still latest. The availability should be ensured in stage 3. Now, same way for load, we have 2/3, meaning that the operand usually is required in stage 2 and latest by 3. For branch, it is 2x2. That means there is no option of delaying it any further. Now, the rest of the entries in the columns are very interesting. For example, for ALU and ALU intersection, which is 4/1, it means that ALU instruction followed by another ALU instruction, one is writing, the other one is reading, then latest we should have a maximum distance between the two instructions, which is 4. And you will see that for all these instructions, the maximum distance required is that of 4 stages. So one entry is 4. However, 4/1 now means that if there is a first ALU instruction, for that it has written a data into register Z4, which is available in stage 4, and we need it in stage 3. So the distance would be 1. So therefore, this calculation is very simple. The numerator 6 minus 2 is 4, and denominator is 4 minus 3, which is 1. So it's very interesting to note that for all the ALU instructions, we have a typical distance of 4 and a minimum distance of 1, except for the branch where it is 2. For the load, we have 4/2, so load and ALU, two instructions, would have a minimum required distance of 2. Now note that absolute minimum in any case would be a distance of stage 1, which indicates 4/1. So with this concept from this table, we understand and see the interaction between different classes of instruction. For forwarding a data from one stage to the other stage, this table would be quite helpful, and we will be able to see the interaction of different instructions. Ideally, we needed interaction of different instructions, which could be up to 32. However, we have classified all the instructions into four different classes: ALU load, branch, and load address. And for these four different classes, we have calculated the corresponding distances. Now this slide indicates the repetition of stall instruction. We have two ALU instructions: add R1, R2, R3, followed by add R2, R3, R4. So therefore, one add instruction adds up the contents of R3 and R4 registers, places it into R2, and this R2 is one of the operand registers for the next instruction. So if we had to follow the detect and stall, we needed to put 3 no-ops in between. However, if we use data forwarding, then only the add instruction, as soon as it is in stage 4, we can place the next instruction into stage 3, take the data from Z4 and provide it as an input through an additional multiplexer placed through some hardware, appropriate hardware, and give it as an input to the ALU unit for the next add instruction. The result would be that no additional bubble would be required in this case, and no op operation could be avoided. In such a way, the pipeline would be faster. So the different instructions going through the pipeline would be executed faster as compared to if we had used a stall operation. Now in our last example, we have seen that by using data forwarding mechanism, the no-ops could be avoided. In some cases, we could completely eliminate these bubbles, or we could minimize if so required. Previously, if we needed 3, we could make it 2 or 1, or in some cases make it 0. So as compared to stalls, the mechanism of data forwarding is more elegant, and this would give a higher performance, higher throughput of the pipeline. Now what is the consequence? To implement data forwarding, we need to have some more hardware. And what would be the consequence of adding this hardware? We need to have wider registers. For example, the IR registers in stage 3 and 4 would still require to have some additional information in order to tell us which particular stage we are talking about and where to feed the data back or forward the data. So as a consequence, we need to put in some additional hardware in the form of multiplexers, right? And some additional control signals would be required, and we could maybe require wider or more number of bits for registers like IR. But still it is worthwhile adding this hardware into our SRC processor and overcoming the data hazard by putting a data forwarding mechanism. Now let us look how this mechanism of data forwarding is written by using RTL statement. Now this conflict or data forwarding could be required by resolving the hazard the hazard could be between stage 2 and 3, stage 2 and 4, and stage 2 and 5. And as in the previous case of stall, the detection would remain exactly similar. However, the correction would be that we update the registers. So in the RTL statement, the first part of detection would remain similar. However, the second part would change, and that we can see in more detail on the following slide. This slide shows RTL for data forwarding. The first column indicates the dependence. We have two cases, dependence between stage 3 and 5, and the second example is for dependence between stage 3 and 4. For 3 and 5, the condition or hazard detected would be ALU5 and ALU3. So that means we have an ALU instruction in stage 5 and an ALU instruction in stage 3. If this condition is fulfilled, then we further check if the destination register of ALU instruction in stage 5, that is RA5, is equal to RB3, where RB3 is the operand register for the instruction in stage 3. So that means if the instruction in stage 3 needs the results written by or given by the stage 5 ALU instruction, then what we do, we take the contents of Z5 register, Z5 buffer register, and put it into X. X in this case is input to the ALU unit fed through an appropriate multiplexer, which you will see in one of the following figures. Now, comma indicates the concurrence, or that means the next instruction is simultaneous, or in this case, these two are actually disjoint conditions. So the second condition which is checked is register RA5 is equal to RC3, meaning that the register RA5, which is a destination register in stage 5, is equal to RC3, which is one of the operand registers in stage 3, which is also an ALU instruction, and not immediate 3. That means that we do not have an immediate operand in stage 3. Then what is to be done? If this condition is true, we take the contents of Z5 and feed it to the second input of the ALU, again through the multiplexer, which is indicated as Y in this instruction. The next stage, stage 3 and 4 dependence, is exactly similar except for the fact that now instead of 5 we have stage 4. So I'll read ALU4 and ALU3. That means in stage 3 and 4 both the instructions belong to ALU class. Then we check the destination register in stage 4, RA4. If it is equal to RB3, then we transfer the contents of register Z4, buffer register Z4, into X, and then simultaneously we check the contents of the value of register RA4, the destination register for stage 4, if it is equal to RC3 and the operand is not immediate in stage 3 and not immediate 3, then we take contents of Z4 and place it into Y, which is the second input of the ALU unit. For both these stages 3 and 4 and 3 and 5, the first part ALU5 and ALU3 or ALU4 and ALU3 indicates detection of hazard, and the second part, the action Z5 transfer to X or Z4 transfer to X or Y, indicates the data forwarding. So this is a very compact representation of data forwarding using the RTL notation. After having an understanding of the RTL description for detection and then forwarding of data, let us now look into how we will have additional hardware for our SRC processor. Conceptually, what we need: first part, for detection, we would need a combinational logic, or it would be just a logic circuitry to find out, for example, if in stage 2 and 3 or 3 and 4 or 3 and 5 we have ALU instruction, or under what conditions there could be a hazard. So a combinational circuit, and then output of this combinational circuit would invoke some action, and this action would be forwarding of data. Data would be taken from some register and it would be buffered through a multiplexer into an ALU unit. Let us have an example and see in the following slide the additional hardware along with the other hardware in all the 5 stages. Comparing it with one of the previous figures, you will be able to figure out what is the additional hardware in this particular diagram. Now, looking at this slide, we clearly see that we have 2 additional units, one between stage 3 and 4 and the other one between 4 and 5. And both of these are identical, and we have named these as hazard detection / forward unit. The input to these hazard units would be coming from IR registers. That means for the interface between 3 and 4, the input data comes from IR3 and IR4, and for the next one between 4 and 5, the data input would be from IR4 and IR5. Now, the forwarding of data at the output would be the data is taken from Z4 and it is fed into the multiplexer which is just numbered as 6 and 7, and the corresponding control inputs are MP6 and MP7. So for the first unit, the data is forwarded from the buffer register Z4 into the input of multiplexers, which we have called X and Y as input of the ALU unit, and actually these are the outputs of the multiplexers. So these 2 multiplexers in the routine, in the absence of a data forwarding control signal, would take data from X3 and Y3 and put it onto the ALU unit as in the previous instructions. However, in the case of data forwarding from stage interface of stage 3 and 4, the data X and Y would be the output of register Z4. Whereas in case of a hazard detected between stage 3 and 5 by this unit, which is at the interface of 4 and 5, based on the input from IR3 and IR5, the results of Z5 would be passed on to the input of ALU unit as X and Y through again the 2 multiplexers MP7 and MP6. Let us just summarize what we have done so far for the design of a pipeline, and with reference to our SRC processor we have illustrated. The first thing was we defined a pipeline, the number of stages. So as a typical example, we took 5 stages. We defined the operation of each stage. Like we said, the first stage would be just fetching the instruction from the memory, second one fetching the operand, third one the ALU operation, and so on. Now this pipeline could be different for different processes. What we have done for SRC is just one example to illustrate the concept of pipeline. Second important step towards the design was to classify different instructions into groups or classes. For our example, we discussed 3 main classes. We said all the instructions could be grouped into either the first category as arithmetic logic unit or ALU instruction. Secondly, we could say load or store instruction. And the third category was the branch instruction. Once we have defined the classes of instructions, we need to map these instructions into different stages. That means what would be the additional hardware required at each stage and how the operation or the processing of data would take place in each stage. So one by one for each of these 3 classes, we discussed and saw what are additional buffer registers required at the interface of each stage and what are the multiplexers required. And then finally in the next step, we combined completely and defined the complete data path for the pipeline. That means starting from stage 1 up to stage 5, we defined using a convention. We numbered stage 1 as 1 and the last one as 5 and placed and interconnected all together the different components, different hardware components, and that defined the data path. Next step in the design was to define the control signals. What are different control signals required? At what stage would it be required? And what particular data element would be activated? Like it could be a control signal for a multiplexer, it could be a control signal for reading or writing into a register, or it could be defining an ALU operation as a control input to the ALU unit. Finally, the last step was to define the hazards and overcome these hazards. And that was done by introducing some additional hardware to detect and then to correct these hazards, either by stalling the pipeline or by using the data forwarding technique. We also discussed that if we do not provide the additional hardware for resolution of these hazards, there could be another possibility, and that could be left to a compiler writer. So that would be a software solution instead of a hardware solution. We did point out and we said that the software solution is usually slow and it could lead to more errors, and the interaction between a computer architect or designer of the CPU and the compiler writer may not be very good, and therefore usually an additional hardware provided into the pipeline chain would be a better solution for resolving the data hazards. So that brings us to a conclusion or the summary of what is a pipeline and what are different design steps into a pipeline. Just to give you a feeling of the throughput improvement in a pipeline, let us look in the next slide with the help of very simple calculations what we could achieve for this particular 5-stage SRC pipeline architecture, how much throughput could we obtain. Let us now make some quantitative estimates of the performance improvement which could be achieved through a pipeline design. Assuming that to a first approximation, the clock periods are the same for unpipelined and pipeline design. The equation for speed up without and with a pipeline, the performance improvement could be written as percentage speed up is equal to IC, which is instruction count, into CPI, the clock per instruction on the average, multiplied by tau, which is the clock period, and this figure is without a pipeline architecture. We subtract minus the same figure with a pipeline and divided by, in the denominator we have the same figure, the base is with pipeline, and just multiplied by 100. Now again, assuming the total number of instructions are the same in both cases, CPI with and without, that would be the result, and tau also assuming to be the same. Result is CPI without a pipeline minus CPI with a pipeline divided by CPI with pipeline. If the average CPI for a unibus unpipelined design is 5, that means we needed 5 clocks to execute one instruction on the average, then the improvement by using a pipeline would turn out to be 400%, which is a tremendous improvement. However, if we take a factor in the loss of performance due to the pipeline stalls, assuming that there is one pipeline stall for every 4 instructions that are issued, this would mean that 5 clocks for 4 instructions are required, and we have a 5 divided by 4, which is 25% additional CPI, and based on this the throughput would be 375%, which is still a tremendous improvement in the throughput. As a conclusion, we definitely see an advantage in using a pipelined architecture, and that would give us an improvement in the throughput, and this improvement would depend on the dependency among different instructions, and a good compiler would try to rearrange the instructions and have least dependence among the instructions, and based on this the throughput would be 300%. Now, after discussing the pipeline, generally we feel and we understand that to increase the throughput, first solution could have been to increase the clock frequency. This is not in the hands of a computer architect. This is fundamentally dependent on the technologists. So the technologist defines what would be the maximum clock frequency that could be used. Secondly, with the help of a pipeline, we just sequentially provide a pipeline for issuing the instructions in a sequential manner, and a number of stages are just executing different instructions and thereby giving us a higher throughput. There is still another method of improving the throughput, and that could be achieved through a parallelism in the instructions. That means we could have more than one ALU, for example. A hardware could be provided, multiplied in such a way that we could process and issue the instructions in parallel and have a higher throughput. And that is what we understand by the architecture of instruction using the parallelism in the architecture. Now, there could be different possibilities. Either we could have a concept of what is called a superscalar, or we could implement that parallelism through a very large instruction word. We will look into more details with the help of a few slides later, but first of all, let us see what is the basic concept behind and how could we compare this particular concept of parallelism with the concept of a pipeline. Now, in the case of a pipeline, usually we have a limited hardware, and hardware unit, for example, ALU is 1. And in the case of parallelism, we provide more than one arithmetic unit. We could divide, for example, have one floating point, another one for fixed point, and similarly for calculating the conditions or branches, we could have more than one unit. And this is the concept of what is called a superscalar. Now, this scalar and vector comes from a very old terminology. In the case of scalar, we say that just one instruction is executed at a time, whereas a vectored instruction, we have different parts of one instruction or different parts of an arithmetic are implemented simultaneously. Like if we have a complex, for example, number, we say there are two parts, a real and imaginary, and if we have two units, we could say it is a vector unit with a dimension 2. And similarly, if we have 3, it could be a vector 3 unit. In the same way, we say a superscalar architecture would be one where we provide more than one unit, like more than one arithmetic logic unit. Comparing it with the conventional pipeline architecture, we see that the hardware requirement for the superscalar architecture would be much higher as compared to that of a pipeline. So therefore, in the pipeline, we feed the instructions sequentially. Whereas in the case of a superscalar, we have a parallel feeding of the instructions. So different instructions are fed into different units simultaneously, and the results could be then manipulated in a way so that they are consistent. Now, comparing with the pipeline, there's no conflict. We could combine the two concepts together. So for each, let us say, a parallel branch, we could still have a pipeline architecture implemented. So the total structure could be a superscalar still using for each of its branches a pipeline concept could still be utilized. Now, in the case of a very large instruction word architecture, we have an instruction length which is quite large, for example, 64 bits instead of 32 bits, or it could be still higher. This slide highlights the differences between pipelining and instruction level parallelism. As we said, in the case of pipelining, we have a single functional unit, whereas there are multiple functional units in the case of instruction level parallelism. For pipeline architecture, the instructions are issued sequentially, whereas for instruction level parallelism, we issue the instructions in parallel. For pipeline architecture, the throughput is increased by overlapping the instruction execution, whereas in the second case, the instructions are not overlapped but are executed in parallel in multiple functional units. Very little extra hardware is required to implement pipelining, whereas multiple functional units within the CPU are required for instruction level parallelism. There are two approaches to achieve instruction level parallelism. One is to have superscalar architecture, a scalar processor that can issue multiple instructions simultaneously is said to be a superscalar. A VLIW architecture, or a very large instruction word processor, is based on a long instruction word. A superscalar machine has following typical features. It has one or more integer units, floating point units, and branch prediction units. It divides instructions into three classes: integer, floating point, and branch instruction. In a superscalar architecture, a number of instructions are fetched simultaneously and then are routed to different units. Now, in the case of branch prediction units, the branch prediction unit predicts or speculates the address to which the next instruction or next branch instruction needs to be routed to. Now, in case that branch prediction unit speculates the next address wrongly, then it is discarded. So idea is that ahead of the branch instruction, we could find out a condition and know where to execute the jump or to which address the program counter should point out. So this could be wrong, but still the chances are taken, and there is a probability that we try to calculate all the possible conditions, and based on these conditions, the prediction unit, the branch prediction unit, predicts the next address, and that address, if it is right, it is kept intact, otherwise it would be discarded. So in the case of superscalar architecture, the architect would define how many different functional units are available, like how many integer units are there, how many floating point units are there, and how many branch speculation units are provided in the case of a superscalar. Some of the example processors using superscalar architecture are DEC Alpha 21164 or Intel P6 or Power PC 601. Now, the details of the superscalar architecture for these particular processors are given in your book, and you can just see how many different units are available in each case. But the main idea remains that out of the parallelism, the throughput is increased. Now, the example of a VLIW is a typical processor which is manufactured by a tri-media company, and we have a very long instruction word, and it could be up to from 64 or 128-bit long. For a VLIW architecture, we could perform the integer and floating point operations or transfer of from one register to the other register more efficiently, because the data bus in that case or address bus would also be wider, and the arithmetic operations could be done more efficiently, achieving a higher throughput. However, the branching is not so efficiently implemented in a VLIW architecture. Today we have discussed in detail the hazards associated with the pipeline architecture. We also discussed how to resolve these hazards. We discussed two methods of resolution. One is to introduce stalls, or second technique would be forwarding. We looked how to describe in RTL fashion these hazards, the detection of hazards, and then the resolution of hazards. We just had written the RTL statements both for stall as well as for the data forwarding situation. Now, we said that in the case of a pipeline architecture, the main problem of the hazards could be resolved either through hardware or through software. Leaving it to the compiler writer would not be a very good choice. Usually we provide additional hardware in the case of pipeline. Now, introducing this additional hardware in the form of some multiplexers or some additional registers would be a very good choice, and that would expedite the throughput. With some examples, we discussed how the throughput would be increased in the pipeline. Now then we said there are other alternates like using a superscalar architecture and the very large instruction word architecture. And there are processors being used presently for both of these architectures. However, we could combine these techniques together. That means a VLIW processor could still use a pipeline concept individually, or a superscalar could also have, along with different branches, a concept of the pipeline being implemented. Now, in the case of a superscalar, we just discussed that the parallelism of the instructions by providing multiple units could give us a higher throughput, and we could have the integer unit, the floating point unit, and the branch prediction unit. So there could be a number of instructions fetched together, and based on the opcodes, we could divide these instructions into different units. Similarly, the branch prediction unit could just process a number of branch instructions and calculate or speculate or predict the addresses for the next instruction or next address where the execution should be forwarded to. Now, these concepts altogether would give us a higher throughput. So it's the choice of an architect that which technique to combine, where we could combine a superscaling concept with the pipeline concept to have a higher throughput. Now, for today, we stop here and close the topic of the pipeline architecture and the superscalar and VLIW. For today, that's all. Till next time, Allah Hafiz.